let's do a few examples before we continue on. So, with example 1, let's write the equilibrium expressions for example 1, which is barium sulfate dissolving into the barium ion and the sulfate ion. Calcium carbonate basically decomposing to calcium oxide and carbon dioxide gas. Iron reacting with water vapor become basically rust and hydrogen gas. So the first one, we're just going to do Kc, and for numbers 2 and 3, we're going to do Kc and Kp. Alright, so let's do the first one. Remember, it's products over reactants. But notice I have a solid, so that's not going to be incorporated into our expression. So what we would have is we'd have Kc is equal to my barium ion concentration times the sulfate ion concentration. Okay? For the second reaction, we have a solid here. Calcium carbonate goes to calcium oxide solid plus carbon dioxide gas. Okay, so again, K, products over reactant. So Kc, notice these are solids, is only dependent upon my product, the CO2 concentration. Kp would be the partial pressure of CO2. And that's it for this one. Okay, because these are solids, they don't get incorporated. The last example is taking iron plus water, vapor, right, and formed rest Fe3O4 solid plus hydrogen gas. Okay, so, and in this case, Kc would be products, so concentration of hydrogen gas, but to the 4th power. That's a solid, so that doesn't get incorporated, divided by reactants. The concentration of water vapor to the 4th power, and that doesn't get included because the iron's a solid. Kp is just going to be the partial pressure of hydrogen gas to the 4th power, divided by the partial pressure of the water vapor to the 4th power. Okay? Now, what would happen if we didn't have this in the gas phase? So what would happen if we had a reaction like this? Same thing, but now it's not water vapor, but it's liquid water. So what you would find is that because this is a liquid, it does not get incorporated into my equilibrium expression. So in this reaction, just because I have a change in state, it's only dependent upon my hydrogen gas. Okay, so those are some examples using heterogeneous equilibria reactions. Okay? So, we know how to interpret K. We also know how to write our expressions. Let's start doing some calculations. Okay. So let me write down the types of calculations you're going to encounter with equilibria, and then we'll go through and do the examples. So one is calculate or determine K. And we have two ways we can do that. You are given all the equilibrium values. Okay, and they can come in various forms. So if you're given moles and volume, then you're going to have to get your concentration. So be sure that before you calculate K, all these values are either in concentration or partial pressure. Okay? The other possibility that you're going to encounter when you're determining K is you're given the initial values. And one equilibrium value. Okay, so when we talk about initial values, remember when we had those reactions in the very beginning with the discussion of equilibrium, and we started off with initial values, and then over time it then reached equilibrium, and then the ratio doesn't change. So what you're doing is we're saying we're going to give you what we started off our experiment with, but then over time we're going to reach equilibrium, and we have one of the equilibrium values. So that's one type of calculations that we can do, determining K. The other type of calculations that we often encounter, okay, is determining equilibrium values. And when we do determine our equilibrium values, what we are is we are given, or you can look up in your appendix, your equilibrium constant and the initial values. Okay, and any additional calculations extend from either once we get our equilibrium values, getting a specific component, kind of like just doing your unit dimensional analysis, or getting to the point that we can get our initial values. All right, so let's do an example. Okay, so let's do our first example. Our first example is actually determining the K, in this case it's going to be Kp, for the Haber process, which is the reaction of nitrogen and hydrogen to form ammonia. And this is occurring at 472 degrees Celsius. So the equilibrium partial pressures are for hydrogen 7.3 atmospheres, for nitrogen 2.46 atmospheres, and for the ammonia 0.166 atmospheres. Let's go ahead and calculate Kp. So remember, is products over reactants. So at Kp, it's going to be equal to partial pressure of ammonia squared divided by the partial pressure of nitrogen and the partial pressure, that's an N2, and the partial pressure of hydrogen to the third power. Okay? So if we just plug in our values, we said it was going to be of ammonia was 0.166 atmospheres squared. The nitrogen was 2.46 atmospheres. And the hydrogen was 7.38 atmospheres to the third power. So Kp 0.166 squared divided by 2.46 divided by 7.38 cubed and we get something like 2.78, 2.79, this is 2.786, 79 times 10 to the minus 5. Okay, so my question for you is this: not only do we calculate Kp, but my question is, does this reaction lie to the right or to the left? As you can see, because my value, this is much less than 1, I'm going to lie to the left. Okay. So, let's do another example. And in the second example, okay, we're going to determine K, right, from initial values and one equilibrium value. Okay, so if we do that, let's do this one. All right, so we have the reaction. We have bromo chloride reacting with itself to form bromine gas and chlorine gas. Okay, and this is at 500 Kelvin. All right. We know that the partial pressure of my bromine chloride gas, okay, is equal to 0.500 atmospheres when setting up the reaction. Okay, and once the reaction reaches equilibrium, the partial pressure of my bromine chloride gas is equal to 0.045 atmospheres. So we're going to determine, in this case, Kp. All right. So now that you have all the conditions, we're now going to introduce you into what we call the ice table. All right. So let me go ahead and erase this. What does an ice table stand for? So the way we're going to do this is, one, I'm going to write the reaction. Okay, so let me write it over here again. Two, you have to write your K expression. For this case, I'm going to do Kp. All right. I'm going to write it over here. Partial pressure of bromine times the partial pressure of chlorine divided by the partial pressure of bromine chloride squared. Okay. And then we're going to do the ice table. So what does I stand for? I stands for your initial conditions. C stands for the change as the reaction proceeds. And E stands for your equilibrium values. And just remember, when you do an ice table, your units must always be in molarity or atmospheres. Okay. Are there shortcuts? Have you ever seen it where people say, oh, you can do it in moles? My suggestion is to avoid the shortcut. There are reasons that can work sometimes, but it's not going to work all the time. And you're better off making sure you're in molarity and atmospheres, just to be consistent and just to not have to worry about backtracking to find out what happened. So we said my initial partial pressure for my bromine chloride, 0.500 atmospheres. And I'm going to put 0 here, because basically that's what I used to start my reaction. So when I do this, some of this is going to dissociate and it's going to form bromine and chlorine. So how much? Well, let's take a look. When it's done, okay, I had 0.040 atmospheres. So how did I go from 0.5 to 0.040? I lost 0.460 atmospheres. This is how much material reacted and became bromine and chlorine. Okay, so look at my stoichiometry. I have 2 here and I have 1 there. So if I had 0.460 atmospheres of my bromine chloride, and I want to convert that to bromine, then you use your stoichiometry, right? So for every 2 atmospheres, remember we were talking about gas laws, okay? So for every 2 atmospheres of this bromine chloride, or bromine chloride, I'll only get 1 atmosphere of bromine. Okay. Now, can I do this? Well, it turns out, if we look at PV equals nRT, we're in the same flask, so the volume's a constant and the temperature is a constant. We already said this is being run at 500 Kelvin. So these two are constants. So the only change is if I have a change in pressure, in partial pressure, that's going to be because I had a change in the number of moles. So in that case, I will only form 0.230 atmospheres worth of bromine. Okay, so you use your stoichiometry. So if I lose this much, then I only form half here, and I only form half here. So you're just going to add and subtract those out. Okay? So now that we have our equilibrium values, so once you know one equilibrium value and your initials, you can derive the rest. Now that we know all of our equilibrium values, we can go ahead and plug it in our formula and calculate out our K. So Kp is equal to 0.230 times 0.230. All of this is divided by 0.040 squared. What we get is Kp is equal to 33. So, does it go to completion? No, but it does lie. The reaction lies. No. To the right. Okay, because K is greater than 1. All right, let's talk about, before we get into determining our equilibrium values, we do need to talk about how do we know which way things are going to go? How do we know how to set up to look for equilibrium values? Okay. So, let's give you an example of what I mean. Let's just go ahead and say, we're going to take something like acetic acid, and it's going to dissociate to H plus and acetate. The question is, if I'm not at equilibrium, did I add a bunch of this and it's going to go to the left? Do I have a bunch of that and it's going to go to the right? Do I have a mix of all of it, and which way is it going to go? We don't know. We're not at equilibrium, and I haven't told you what I have initially. So this is how it works. When you are not at equilibrium, we need to determine which way the reaction goes. So what we're going to do is we're going to use a reaction quotient, Q. Okay, and how do we use Q? Well, it turns out the expression for Q is products over reactants. So what differentiates between Q and K? Because K is also products over reactants. So how can you tell? When you put in your values, your partial pressures, your concentrations of products and reactants. These are non-equilibrium values. Okay, if you don't know that you're in an equilibrium situation, then the first thing you're going to do is use Q, and then we're going to compare it to K. So, in the most general terms, if you have your general equilibrium equation, Q is equal to C to the power of C, D to the power of D, A to the power of A, B to the power of B, and the values are just at non-equilibrium. Or let me just say not at equilibrium. Okay, so this is really crucial that you differentiate between the two. All right, so let's continue in just a moment. Okay, so let's talk a little bit more about our reaction coefficient, Q. All right, remember when we calculate Q is calculated as the products over reactants. Okay, so if you look at the expression, it's going to look exactly, the same as K. So what was the difference? Well, if Q, we're talking about non-equilibrium, okay, conditions. And if you look at it, then the question is this: how do we determine whether or not we're at equilibrium or which direction my reaction will shift? So if Q is less than K, then it has to go, the reaction has to go to the right. It has to create more products in order for it to reach equilibrium. If Q equals K, then you're at equilibrium. If Q is larger than K, then I have too much product, and I need to go to the left to decrease the amount of product and increase the amount of reactant to get to K. So, when Q is less than K, reaction lies to the right. When Q is greater than K, reaction lies to the left. And when Q equals K, basically, you're at equilibrium. So let's take a look at an example. So let's take a look at this reaction. You take your sulfur trioxide, and it decomposes, give you your sulfur dioxide plus oxygen. And this is at 1000 Kelvin. Alright, and suppose we have this reaction where my partial pressures 0.16 atmospheres, partial pressure of sulfur dioxide is equal to 0.41 atmospheres, and the partial pressure of oxygen is equal to 2.5 atmospheres. And we know Kp is equal to 0.338. So the question is, what is Q? Okay. And 2, which direction will the reaction proceed? It's not at equilibrium. Okay, so let's take a look. Q P is equal to partial pressure of oxygen times the partial pressure of sulfur dioxide squared divided by the partial pressure of sulfur trioxide squared. Okay, so now that we know that, let's go ahead and calculate it out. QP is going to be equal to 2.5 times 0.41 squared divided by 0.16 squared. So QP is equal to 16. So we know that QP is greater than K. So the reaction is going to go left. So what does this mean? So this means that when I am trying to reach equilibrium, this partial pressure will increase and these two will decrease. Okay? So let's try some calculations now. Let's start off with, okay, when we do calculations to determine like equilibrium values, so concentrations or partial pressure, okay, what we're going to be doing is from our equilibrium constant and the initial conditions. So here's another type of calculations that we can use with Q. Alright, so let's do this example. A 1 liter flask contains 0.50 moles of hydrogen gas and 2 moles of iodine at 448 degrees Celsius. Kc is equal to 50.5 at this temperature. Okay? And what we want to know is determine the equilibrium concentrations of hydrogen, iodine, and hydrogen iodine given. And here's our reaction. We need to know our reaction, right? H2 gas plus I2 gas forms 2 hydrogen ions. And this is going to be at 448 degrees Celsius. Okay. So what are the steps that we need to do? Well, as we talked about before in another example, first thing we do, okay, is write our reaction. Okay, so we need to know what we're working with, so let's get that done. Okay, H2 plus I2 forms 2HI, and that's at 448 degrees. Okay, then we write the K expression. Okay, which I'm going to put over here. And our K expression is this. K is equal to concentration of HI squared divided by the concentration of H2 and the concentration of I2. Okay. 3. You're going to write your ice table. You're not going to fill it in yet, so write the ice table. Just get that all organized. So, my initial conditions, the change, and then my equilibrium values. Okay? Now what we're going to do is we're going to fill in the table. Okay? So when we fill it in, let's take a look. We're given moles, and 2, and a volume. It's a 1 liter flask. Okay? But we're not given concentration, right? So we need to determine the concentrations. And we know that molarity is equal to moles of solute over liter of solution. In this case, it's moles of solute over the 1 liter flask, the volume. Okay, because the gas is going to take the whole volume. So it turns out that this is still 0.5000 molar. Okay? Turns out that this is still 2.00 molar, and we have no HI. Okay? That's the first order of business. The second order of business, now that you have your concentrations, is this. When you look at Q, so Q is going to be equal to products over reactants. So it's going to be 0 squared over 0.5 and 2.0. Okay, so Q is 0. So Q is less than K. And K, remember we were given K. K is equal to 50.5. So, why is this important? That means we're going to lose product. That means my reaction goes to the right. So if I lose reactant, my stoichiometry is I'm going to lose some amount of H2, I'm going to lose some amount of I2, and I'm going to gain 2 times that amount. Okay? It's going right, so I'm forming more product. If my reaction were going left, then that would be plus, plus, and that would be minus, because I have to go in that direction. Okay, so when we're done here, it gets to the point where we're so used to seeing Q equals 0 and the reaction going right, this becomes instinctive. But it's really important to stop and take a look at it and make sure you know it's going to the right. And just for space, I'm going to reduce, no, I might be able to put this, and this is 2x. So the problem is this, from my ice table, in the previous example, where I was given an equilibrium value, I could fill in the table with numbers. In this case, I only know that I'm losing some product and losing some reactant and I'm forming product. So I'm given these expressions. So when you're given K and you're given your initial, what you're going to do is this. You take these expressions and you put them right back in here. So let me go ahead and do that. So now that we've filled in the table, you're going to solve for the change. Typically that's x. Okay? Now remember, the question is, what are my equilibrium values, not what x is. But we need to find out what x is so we can solve for it. Okay? So let's go ahead and do that. So we know Kc is equal to hi squared over h in I. So if we look at this, 50.5 is equal to 2x squared divided by 0.5 minus x and 2 minus x. Okay, so I'm going to multiply both sides by this. Okay, so what we have here is we're going to have to solve the quadratic equation, and that's 4x squared. Okay, so now the rest is really going to end up being just doing a bunch of math. So let me see what we can do here. So we have 50.5, and I put it in black now because all we're doing now, we've done our chemistry part, and now this is just doing the mathematical part. So 0.5 times 2, it's going to be 1, minus, so that's a minus 2.5, 3x, okay, plus x squared is equal to 4x squared. So 50.5 minus, and then let's do 2.5 times 50.5 minus 126.25 x, all right, plus 50.5 x squared, and I'm going to subtract both sides by 4x minus 4x squared, and this will be equal to 0. So let me rewrite this. This is 46.5x squared minus 126.25x plus 50.5 is equal to 0. So now we have to use our quadratic equation. Okay, so I'm going to leave this up here. Our quadratic equation, remember, is x is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a. Okay, and we know this is equal to a, this is equal to b, and that's equal to c. So let's just plug in our numbers. So x is going to be equal to a minus negative 126.25. Okay, I might need more space, so let me just go back. Okay, plus or minus the square root, okay, of my negative 126.25 squared minus 4a is 46.5, and c is 50.5. Okay, all of this is going to be divided by 2 times 46.5. So what do we have? 26.25, square that, and then minus the 4 times 46.5 times 50.5 equals, so I get 100 minus times minus is positive, 126.25 plus or minus the square root of 6,546.06 divided by 2 times 46.5, 93. Okay, so let's just go ahead and continue to solve this. Take the square root of that, 126.25 plus or minus 80.91 divided by 93. So we're going to have two solutions, right? 126.25 plus the 80.91, okay, divided by 93. So one solution is 2.23, okay. The other solution, 25 minus the 80.91 divided by 93 equals, and this is 0.488, okay. And x, remember, we were looking at, basically, we were looking at pressures, so this is, or concentration, so these are in concentration, so 2.23 molar, 0.488 molar. So then the question is, which is the correct solution? Okay, so let's go back to our expressions. We said for the hydrogen gas, that was going to be equal to the 0.5 minus x, 0, okay? For the iodine, it was going to be equal to 2 molar minus x. And for HI, it was going to be equal to 2x. So 0.5 minus 2.23 is a negative number, and you may not have a negative concentration. So it must be 0.488. Minus 0.488, and that's going to give me a 0.012 molar. That's how much my hydrogen gas concentration will be. In this case, 2 minus 0.488, that's going to be equal to the 1.512 molar. And for my hydrogen iodide gas, that's going to be 2 times 0.488. That's going to be equal to 0.976 molar. Okay, so in the event that when we solve our quadratic equation, we get two solutions that look viable, once we go back to our initial expressions, we can determine which of those values is legitimate. Okay, So in this case, this is what we've done. We have determined our equilibrium concentrations based on knowing what K is equal to and our initial conditions. And the way we do it, we go through the ICE table, we get expressions, put that into our K expression, and many times we have to solve the quadratic. And this is one of those cases. Okay, so let's do one more example. And what we're going to do is we're going to get the equilibrium concentrations of each of these gases, okay, in this equilibrium reaction. So we know we are given that Kp is equal to 0.497, okay? And we also have our initial pressures. And the initial pressures, we charge this, okay, with 1.00 atmospheres, okay, of my phosphorus pentachloride. And I want the equilibrium pressures. Okay, so what did we do? We already wrote down our equation. Let's write down our K expression. In this case, it's going to be Kp. That's equal to the partial pressure of phosphorus trichloride times the partial pressure of chlorine gas divided by the partial pressure of phosphorus pentachloride. Okay, so and then we've done our reaction, we've done our expression. We now need to fill in our ICE table. In this case, we started off, we're given everything in atmospheres, and that's what we're after, so this is good. We started off with just 1 atmosphere. You're not given any phosphorus trichloride, and you're not given any chlorine gas. So when the reaction proceeds to reach equilibrium, since Q is going to be equal to 0, and Q is going to be less than K, our reaction is going to go to the right, which means I'm going to lose a little bit of my phosphorus pentachloride, and I'm going to form a little bit of phosphorus trichloride and chlorine gas. So at equilibrium, this is 1 minus x, this is x, and this is x. Okay, so now that I have my expressions, I'm now going to put these expressions into my Kp equation here. Okay, so when I do that, we know Kp is equal to 4.497, okay, and that's going to be equal to x times x, or x squared, divided by 1 minus x. So now we just have to go through and get our quadratic equation. So I'll use a slightly different color. So we know we're just doing the algebra part. And that is, if I take this phrase, this expression, and put it up here, it's going to be 0.497, 1 times 0.4, minus 0.497x. Okay? Get a little more space here. And that's going to be equal to x squared. So 0 is equal to x squared plus 0.497x and minus 0.497. A is equal to 1. This is equal to B. This is equal to C. So let's do our quadratic equation. when we do our quadratic equation, it's going to be x is equal to a negative or a minus b, so minus 0.497 plus or minus the square root of 0.497 squared, okay, minus 4 times a times c, which is a negative 0.497. I'm going to have to move this over so you can see. Get myself some space here. Negative 0.497 plus or minus 0.497 squared minus 4 times 1 times a negative 0.497. All of this is divided by 2a, so 2 times 1. So for my x values, this is what I'm going to get. I have 0.497, okay, square that, and then I have minus 4 times 1 times a negative 0.497, okay, so take the square root of that, okay, and what I get is going to be a negative 0.497 plus or minus 1.495 divided by 2. Well, I don't need to subtract because that means my x is negative. So let's just look at the first value. Minus 0.497, divide that by 2, and I get x is equal to 0.499 atmospheres. Okay? So what does this mean? So when we look at our equilibrium values then, our equilibrium values are going to be this. My partial pressure for phosphorus pentachloride is going to be 1 minus 0.499. So I just get a 0.501 atmosphere. Okay? And the partial pressures for my phosphorus trichloride, which is equal to the partial pressure for my chlorine gas, is going to be equal to 0.499 atmospheres. Okay? So far so good? Now let's go through and see whether or not this makes sense. So the way you check to see if your values are reasonable is this. Where you're just going to recalculate K and see if it matches with the one that we're given. So if I had to calculate K with my equilibrium values, K is going to be 0.499 times 0.499 divided by 0.501. Okay, so this is going to be how I'm going to check. So I take my equilibrium values, put it into my K expression, and when I do that, what I get is I get a 0.497 is equal to my KP. And that is what we started with. So this is good. So then I know that my equilibrium values are correct. Okay? And that we've finished this problem.